All right. Good evening, everyone. We have Rahul and Krishna Kumar. Thanks for joining. And uh, probably we will start and we will maybe more students will join. Okay. So let me check my recordings first. All right. So in week three, we all know what we did. Basically, we continued our discussions on conduction heat transfer, and especially we focused on cylindrical geometry and also spherical geometry, and also we touched a concept called critical thickness. So these are the main focus, and we also solved certain problems related to these uh, these concepts. So what I will do today is I will again solve three questions today, two on cylindrical and one on spherical. Although spherical is not in your assignment, but I thought it would be good to have one question in spherical so that you'll feel more confident in facing such a question. And we will have two cylindrical conductive heat transfer problems. We will solve them. Okay. Before we start, if you have any questions, please let me know. I would, if you have quick questions, I can quickly answer. If not, we will get started with today's session.
Good evening, sir.
Good evening, Basancha. Thanks for joining.
Thank you. Sorry for getting delayed.
No problem, no problem. Don't worry
So,
about it.
could you please summarize just recapitulate the things, the
Right,
principles?
right. So actually, I was just telling that we covered the uh, we continued our discussion on conduction in the week's lecture, right? So
Yes, sir.
we studied cylindrical, spherical, and critical thickness. So I was just uh, reminding that we studied these three topics in the week three, and we will be solving three questions in these topics. That's what I'm telling. Nothing much.
Yes.
All right. If there are no questions, maybe we will quickly get started. So probably maybe since Bas and Jenna also brought it up, maybe I will quickly go through what we did in the lecture also. I hope everyone has gone through the lectures. If not, I can give you a quick recap. So I think we started with the conduction in cylindrical geometry, and then we basically took a strip of a ring, you can say, or a cylindrical strip, and we integrated. We just basically did a heat flux balance, or or energy balance, basically. For that small integral, sorry, infinitesimal small strip, and then we just put the limit to zero, and then we got the differential equation. And then we did the same for spherical also. Before we did, we also, for cylindrical, we also, with heat generation and without heat generation, how the uh, heat flux, temperature profile, how it varies, and what is the general formula, we, you know, kind of derived it. And then, there is some concept called critical thickness, which basically gives a balance between, which basically tells whether conduction resistance is more or convection resistance is more because of increase in insulation thickness. And we studied, we did the same thing for spherical geometry, and also we also did the critical thickness for the spherical geometry, right? And so today's uh, problems are also going to be based on this. Maybe we'll quickly jump into the problems, and if required, we will get back to the notes again and revise it. Okay. So the first problem is going to be about a 3 mm diameter electrical wire insulated by a 2 mm thick rubberized shell with a thermal conductivity which is given 0.13 watt per meter Kelvin, and the wire shell interface the so there is a wire of 3 mm diameter, and on top of it the 2 mm thick rubberized shell, or kind of insulation. Rubberized shell is is on top of this wire, and in between these two wire and the shelf, the wire shelf interface is characterized by the thermal contact resistance of this much. So we actually didn't study contact resistance, or we actually didn't touch up contact resistance in our lectures till now. So basically what it means is, usually we assume that contact resistance is zero, but in here we have certain resistance. So we have a wire, and on top of it you have a stud, and when the heat flows from the wire to uh, this stealth interface, usually we don't consider any resistance, but here we have some resistance. That's what. Okay. And you have a convection heat transfer coefficient at the outer surface of the cell, which is 15 watt per meter square Kelvin, and the temperature of ambient air is 20 degrees Celsius. If the temperature of insulation may not exceed 50 degrees Celsius, what is the maximum allowable electric power that may be dissipated per unit length of the conductor? So what it says, probably if I draw a diagram, it would be more helpful. So you have a wire with a circular cross section whose diameter is 3 mm, and on top of it you have a rubberized shelf whose thickness is 2 mm, not the diameter, thickness is 2 mm. Okay, so this is the rubber, this is the wire actually. So it's a very big wire. Maybe I will draw smaller wire. Okay, this is the wire. um, this diameter is 3 mm. This is the electrical, wire. So it's going to carry current, and if it carries current, it is going to generate heat. And the diameter of this is 3 mm. So maybe I will. Okay, and the thickness of the stealth here, it is 2 mm. Okay, this is the rubberized stealth. It has some thermal conductivity and things like that. Only thing we are telling now is, here you have this interface, right? There is this wire and there is this stealth. So this is wire, this is stealth, and the interface between these two has some contact resistance. So it inherently has some resistance. So usually when you have wire and when you surround it with a stealth, usually what we will have is, we will have small gaps in which air can enter. And if air has entered between them, then you do not have, so these two surfaces are not joined, and if they are not joined, the heat cannot easily pass through. It has to go through the air and then it has to go out. Okay, so basically if this is the wire, if I zoom in, uh, if this is the wire, so this side it's wire, this side it is stealth. Now what happens is, usually we consider these two to be touched one upon each other, but what happens, there will be like small wrinkles or something because of surface, roughness or things like that. So there will be these small portions where you can have air accumulated, or any material accumulated, which will have different thermal conductivity than the wire and stealth. So there is an inherent resistance in between this wire and stealth when they are in contact. That's what we call it, contact resistance, which is given. Okay, so let's write that down. So K of this shale sheath, yeah, is 0.13 watt per meter Kelvin, and the contact resistance between this is 3 into 10 power minus 4 meter square Kelvin per watt. So this is in uh, this is in per unit area. This is for a area. Okay, so you also have heat transfer coefficient. 15 watt per meter square Kelvin, and then you have an ambient temperature of 20 degrees Celsius, and you do not want the temperature of insulation should not exceed 50 degrees Celsius, which means the temperature inside the in your sheath, the rubberized sheath, should not exceed 20 degrees 50 degrees Celsius. Okay, if that is the upper limit you are imposing, then what would be the power or what would be the current that this wire can carry is what you have to find out. So in this case we have asked power, which means what is the maximum heat generated or heat transfer that we can have across the sheath. Okay, that is one thing. And the second thing is they are also asking critical radius of this insulation. What would be the critical radius of this insulation? Okay, so we know how to solve. So this is basically a cylindrical heat transfer, conductive heat transfer problem. Now, um, only thing new is this contact resistance, which is new for you guys. Now, let's say, so how do I go about it? So for first of all, they have said that temperature of insulation may not exceed 50 degrees Celsius. So where it could exceed 50 degrees Celsius? I mean, in which of these
The outside surface of the sea.
outside surface of the sheath? Why?
Because just a second, sir. It will come from the no, no, sir. Sorry, sorry, sorry. So inside, because the heat will transfer from the conductor.
Right,
So
right.
first, that gradually that will decrease towards the outside surface.
Why? Wonderful. You're right.
Yes.
So actually, the temperature would be, you do not want temperature of the insulation to not exceed 50 degrees Celsius. So this is your insulation. So in the insulation where you can have maximum 50 degrees Celsius is where you have the heat entering, right? So heat is entering in this position or in this circle. So the inner surface of the sheath, as you rightly said, will have it can have maximum 50 degrees Celsius. Okay. So if that is the case, so let's say we will call this TS. So TS is 50 degrees Celsius. Then how do we go about it? You can find the maybe you can draw a resistance diagram.
Yeah, here there will be three resistance, sir.
Okay.
One is through contact resistance,
Mm-hmm.
then through the seed material, and then last one is convection.
Okay. So yeah, wonderful. So you will also have convection. H. So you will have it will all be in series. All right. So this is T infinity. Here you will have. So where will you have TS? So which of these terminals will have TS? Should we say TS or we can say TSI so that it will not be confused. This is TSI and the outer surface is TSO. So this is going to be TSO. Now will this be TSI or this one will be TSI?
No, sir. Second one. There is the interface of R contact and R conduction.
Okay, yeah. So you can say that because the contact resistance comes before the sheath, right? So um, you can say this has TSI, and
Ah,
then
ah, ah.
here let's say you have TS dash, which is the surface of the wire. Okay, from wire to sheath you have some resistance. That's what it means. So now, how do we solve this problem? So we just need to find what is the Q going through this. May dissipated per unit length of the conductor. So Q by L basically we can find out. So you already know this is going to be Q times. So since we know TSI and T infinity, we can
Mm.
actually use these two terminals to find the resistance. We can use these two resistance to find the Q, right? So here you no need to bring the contact resistance in it. Okay.
Yes.
All right. So how much is this coming out to be? So let's first find out what is R conduction and R convection. What is R conduction? Since it's cylindrical, you will have l- natural log of
L by L by. So you have cylinder, huh?
this is
Ln by.
cylindrical, right? So yeah.
Huh.
So
By.
natural log of R2 by R1
Yeah.
divided by 2 pi KL. Here we are going to do it for per unit length. So this length can be we can keep it like that. So here what would be R2? So you will have
Up to sir, up to equal to 1.5 plus 2, 3.5.
okay. So this is yeah. So this part is 2. This part is 2. This is 1.5. This is 1.5 plus 2. This is R1. This is R2. So this is 3.5 divided by
3.5 divided by 1.5.
1.5. Wonderful. Divided by 2 pi into Ks. Ks would be 0.13 times L. Okay. L we no need to find. We will just keep it like that. And R convection. So convection, how will it be? 1 divided by h into area of the surface, where area of the surface would be perimeter times the
2
length,
pi RL. 2 pi
2 pi
RL.
r. So h is how much was the h here? 15. 15 into 2 pi into r2, where r2 is 1 divided by 15 into 2 pi into 3.5.
Yes. So L.
Yeah, so L we don't know, right?
Oh,
L is not given in the question.
ah,
Instead,
ah.
what they have asked is electrical power that may be dissipated per unit length of the conductor. So
Okay,
either
that's it.
you can substitute L equal to 1 also.
1. Yes.
You can substitute L equal to 1 also, or you can just keep L and
Okay.
take the
It
L
will
to
be
the other side.
cancelled. It will be
Exactly.
cancelled.
Yeah, it will be cancelled. Yeah. Or what I mean to say is you keep the L like that and
Ah,
then take find Q by L. Q by
yes, sir.
L is
Per
what they are
unit.
asking. So you can directly find Q by L.
Per unit.
Per unit length you can find. Okay. So how much is this if you calculate? So I'm getting something like 1.0373, and this one is this is coming out to be something like 3.03. 15. Please check whether these are right or wrong. Okay, so then you can substitute them in the above
3.03,
equation.
sir. 3.0330.
Okay, 3.0330.
0. Or 0.
330, is it? Okay.
Yeah.
Now, what would be the Q? So you can substitute them here. So TSI is 50, T infinity is 20. So this will be 30 divided by 1.0373 plus 3.033, which is equal to, okay, sorry, this you should have divided by L here. So this whole thing you can, so this whole thing divided by L. So you can write this as Q by L is equal to 30 divided by 1.0373 plus 3.033. Okay, and this will come out to be something like 7.37 maybe watt per meter. So you can notice that they have asked for watt per meter. So energy dissipated per unit length, and this is what we are getting. Okay, all right. So now they are asking what is the critical radius of the insulation. So critical radius of the for cylindrical coordinate, for cylindrical geometry, we already know the critical radius. What would be that? So this is simply K by H, right? Here K will be the insulation thermal conductivity, which is Ks, which is 0.13 divided by 50. How much is this coming out to be? So this is something like 8.67 10 per minus 3 meter, or you can write it as 8.67 meters.
0.008
Correct, 0.008. Yeah. So, sorry, it will be in
millimeter.
millimeter. Yeah. So, what does it mean? So, when I say R critical is 8.67 millimeter, um, what does it really mean? So, can I put thick insulation till 8.67 millimeter, or should I put less than that?
Less. It should be less, sir.
Okay. Why?
Because if you go on increasing, so the convective, uh,
The heat
uh,
transfer will continue to increase, right?
yeah,
Yeah. So let's say if I increase the thickness, so that's what, if you remember, we had this plot. Uh, so we had this plot of Q versus R, Q versus R, and you have R critical somewhere here, right? And at R critical, what do you see? You will see a maximum heat that can be passed, which means until you cross the R critical, your uh, convection mode of heat transfer is dominant, which means the resistance through uh, convection is more, sorry, convection is less, which causes higher heat transfer through convection. So if I continue to increase, let's say if I increase the insulation thickness to 8.67 meters, what can happen? I can actually, increase the Q through the wire. Okay, so I can send more power through the wire, or I can operate it with a higher current, or with higher voltage difference. Okay, so that is what it means. So currently we are at R of 3.5, right? So 1.5 plus 2. So at 3.5, this is 3.5 mm, And what they are telling is if you increase it to 8.67 mm, you will have maximum Q max. Okay, so this is 7.67 watt per meter, and you can have a Q max when you increase the thickness to 8.67 mm. Okay, so 8.67 mm minus 1.5 is like 7.1 mm is the thickness. So currently the thickness is 2 mm, so I can increase the thickness to 7.1 mm, and at that point I still will have 50 degrees maximum temperature will still be 50 degrees Celsius. However, the Q current which I'm passing through the wire can be higher. Is that clear what I'm trying to say?
Could you please repeat it, sir?
Okay. So what does it mean? So for example, we have 7.37 watt per meter of energy that is dissipated through the wire. Okay,
Right, sir.
through the insulation. 7.37 watt per meter is dissipated through the insulation, and the R critical is 8.67 meters. Okay, so if you continue to increase the insulation, what happens? The surface area of convection keeps on increasing,
Yeah.
and if it keeps on increasing uh, until the R critical, we know the heat transfer is going to continuously increase because of the convection. Okay, till here the convection heat transfer is more than the conduction insulation conduction,
Mm. Mm.
right? So Q will continuously increase, the amount of heat you can dissipate will continuously increase. So if I want to increase the current through the wire, then I have to do, if I want to increase the current through the wire, so at this point I am in 7.67 watt per meter.
Okay.
I want to increase it. So let's say if I want to increase it, what should I do? So at 7.67 centimeter, my temperature in the insulation will be 50 degrees Celsius. The inner surface temperature will be 50
Mm.
degrees
Mm.
Celsius.
Yes, yes.
Now, if I increase this, what happens? Now, let's say what I'm doing is I'm just increasing the Q. Okay, I'm not doing any insulation. I'm just increasing the Q through the wire. Okay, which means
Mhm.
there is a lot of Q going out. So what happens? The TSI continues to increase. It will increase more than 50, right?
Mm. Mm.
Now I don't want TSI to increase. Then what should I do? I have to remove more heat from outside. So from convection, I have to remove more heat outside, right? And if I want to remove more heat outside, I need to have more surface area. So I,
Radius should be increased.
increase the area. So that is exactly happening. Okay, but it can happen only to a certain extent, because whatever you are doing is you are adding insulation layers, and once you add insulation layers, the conduction resistance also continuously increases when you add insulation layers, right? So after this point, the conduction resistance will be more, so adding a more insulation layer will not remove the heat outside because of convection, because the conduction has increased. Okay, that much heat will not go through the convection. So that's why it started decreasing basically, right? So now my idea is I want to increase more current in the wire. Which means I want to dissipate more energy through the wire. Then what should I do? Is my question clear?
Yes, yes. Question is clear.
Okay, so basically what I'm trying to say is, uh, you have currently you are at 3.5 mm.
Mhm.
Okay, and at 3.5 mm this is your heat flux, 7.67.
Mhm.
Okay, now let's say if I increase 3.5 mm to 4.5 mm, what will happen?
Heat flux will increase.
Exactly, because the 4.5 mm is still less than critical radius.
Mm. Mm.
Until critical radius, heat flux will increase,
Yes, yes, yes,
right?
yes,
So
yes.
the heat flux reaches maximum at 8.67 mm,
It consists.
right? So I can keep on adding insulation until 8.67 mm,
Yes.
right?
Yes.
For which I will get maximum heat out.
Right, sir.
Okay, for
Mhm.
which I will get maximum heat out.
Right, sir.
If that is the maximum heat out, then that will then I can pass more current through the wire. That's what it
Right, sir.
means,
Right, sir. Right, sir.
right? Does it make
Yes.
sense now?
Mhm.
Should I explain it more?
Beyond that, it will reduce.
Right, beyond that only it can reduce. So if I want to reduce, then I have to go up after that, I have to go beyond critical radius. But
Yes.
if I want to increase, I have to go till the critical radius.
Yes, sir. Yes.
You understand
Yes. Yes.
now? Okay.
Yes, sir.
Okay. All right. Good. Now let's move on to the second problem. So the second problem also now deals with electric current. So the electric current flows through a long rod, generating thermal energy at a uniform volumetric rate of 2 megawatts per meter cube. So this is also cylindrical. So its electric current is flowing through the rod. Now it is not a wire; it's a rod with a uniform volumetric rate of 2 megawatts per meter cube. The rod is concentric with a hollow ceramic cylinder, creating an enclosure that is filled with air. So there is this hollow cylinder inside that the rod goes. In between this hollow ceramic cylinder and the rod, there is a air closure, air filled enclosure. So this is air. Okay, this is the ceramic enclosure. This is the rod. In between, you have a air filled enclosure. Okay, thermal resistance per unit length due to radiation between the enclosure surfaces, which means from the inner area of the rod to the enclosure surface, there will be radiations happening. The thermal resistance per unit length due to the radiation is 0.3 meter Kelvin per watt, and the coefficient associated with the free convection in the enclosure. So since air is filled here, there will be convection going on within the in between these spaces, and that H is 20 watt per meter Kelvin. Okay. Now we are asked to construct a thermal circuit which can be used to calculate the surface temperature of the rod. Okay, and label all the temperature, heat rates, thermal resistance, and evaluate the thermal resistance. So we need to draw a thermal circuit, and then finally we also need to calculate the surface temperature of the rod. Okay, is the question clear?
Uh, Sir, actually, there are two things are given.
Mm-hmm.
One is conductivity, thermal conductivity due to radiation, and thermal conductivity due to convection. That is 20 watt per.
Watt per
So,
meter Kelvin. Yeah,
but in between the metallic wire and ceramic, so there is air. It is filled with air.
correct.
So when it is filled with air and it is not in motion,
Mm.
so whether it will be it will be convective or through radiation.
Okay. So one thing is radiation doesn't require medium. So whether air is there or not, it doesn't matter. Radiation will happen.
Ah,
Okay. So radiation will happen. Now the question is the air is present. Whether and also you should note that they have already said it's a free convection. So what happens is because of heat generated, uh, because of density differences, there will be circulation of air. Okay, although you are not
oh,
sending air in,
okay, 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 okay.
there will be
Right, right.
circulation of air because
Yes,
of
yes.
density
Natural,
difference.
natural circulation.
So the natural
Natural convection.
convection is what is
That
given
is
as H.
deconvection. Yes,
Yeah.
understood.
So there are both the modes of heat transfer are present. One is radiation. It doesn't
Mm-hmm.
matter whether air is there or not. Another is convection. Both are there actually. Okay.
Right, right.
All right. So if that is clear, let's draw the circuit. How will it be? So let me maybe draw it a little more bigger here. So this is the rod which which is carrying the current.
Yeah, diameter 20 mm.
and this is the ceramic cylinder. So from here, um it is the diameter is
20 mm.
diameter is 20 mm, which means the R will be 10 mm.
10 mm.
Okay, so let's say this is R1, and then this is R2, and then this is R3. So R1 is 10 mm, and R2 is, so the ceramic DI is 40 mm, which means R2 is 20 mm,
20 mm.
and R3 is, this is they are given to be 120 mm, so which will be
60.
60 mm. All right. Now, what we have is we also they are also given K of the ceramic material, which is 1.75 watt per meter Kelvin, and H. So now the air present here is circulating inside the enclosure. So there will be a convective heat transfer, which is given as 20 watt per meter square Kelvin. Okay. And in
Yes.
addition, you also have radiation resistance, which is zero point 0.3 meter Kelvin per watt. So which means it's per unit length. It's That's what it means. R times L is what they have given. Okay. Probably you can write this as R times L. Since they have given meter also, I'm just writing it as R times L. Or it's understood. You can write it as radiation. So how will we draw the thermal circuit? Let me also give the uh, temperature. This will be TR, and this will be T. What can we say? T of ceramic. So we can say this can be T S I, and this can be T S
Yes.
O. Okay.
Yeah.
T naught. T naught is given. Okay, so we can write this as T naught, which is 25 degrees Celsius. So outside there is no convection. They are given 25 as a surface temperature. This we can say it as Ti, inside surface. Okay, and we have air which is flowing through it, and we are not pushing the air, but it is automatically natural convection is doing it. Okay, now what will be the thermal resistance? So basically along R you need to draw. What are the resistance you will have?
First one through by conduction inside the metal wire.
uh, Actually we need to,
Oh, sorry,
when
sorry. Sir, temperature, which temperature is given? It is T, outside is given 25.
right, and we need to know only the surface of the rod. So we can assume that Q is coming out. We can
Uh,
actually say that to from TR to T naught we can draw the thermal circuit,
ah,
because electrical wire is generating the heat, and this whole heat is going to come out, right? So you no need to consider the electrical wire here. So you can start from the surface of the electrical wire.
sir, surface temperature of the wire is as, na?
Surface temperature of the
Okay,
wire
okay.
is
Where is it? Okay,
yeah.
okay, okay, right.
Surface temperature of the rod is
Ah,
asked basically.
mhm.
So from TR only we need
Yes,
to
yes,
draw.
yes. So that means we have to draw the circuit.
So this will be TR. So from TR, what will be the first resistance?
T, here to Ti,
Okay, TI. But what are the resistance you have in between? So
and
first thing
that is
is,
convective, convective.
so one thing is we first thing is, let's take one step at a time. For one more thing is, you will have radiation also from here,
Ah,
right? From the rod to the enclosure. That's all. So this is one radiation is there. Okay, so let's say from TR I have radiation to TI. Okay, what are the other? So this is TR and TI. These are the two terminals. In between, what are the heat transfers we have? One is radiation we have. What are the other heat transfers we have?
Convection.
Convection. But where to where convection is happening? So convection has to happen between uh, surface and air. Okay, it cannot happen from surface to surface.
Okay. Okay. So then it should be before that, before radiation.
No, no, no. But so okay, you think about it. So you have a rod here. Let's say if I draw a zoomed in view, um, you have a rod here and you have a enclosure here. Okay, this is TR. This is not changing, and this is TI.
I,
Okay, in between you have air. Air is flowing. Air is I mean it can flow anyway. That doesn't matter. So now what happens? Initially you have this surface. So air is flowing. Let's say you consider air to be some T infinity temperature. Then what happens? From surface to air, there is a convection. Okay. So this is one heat transfer. And from air to this surface, there is another convection.
mm,
Okay. There are two convections in between. You should carefully notice here. So since air is there, so from surface to air only convection can happen. So from the TR, you have one convection. Okay. To T infinity, and from air T infinity you have another convection to the inner surface of the ceramic enclosure.
okay.
Is that clear?
That means you mean to say, sir, the first one from the metal surface to air is through radiation first,
Hmm.
then it will be followed by convection from the, it will be followed by convection till the inner surface of the ceramic.
So okay, so let's forget about radiation for a minute. Without radiation, can you say what would be the thermal circuit? So let's say there is no radiation, what would happen? So from TR you have one heat transfer to air,
Mhm.
so that will be a convection resistance.
Yeah.
It will be till T infinity, and from T
Mhm.
infinity you have another convection resistance
Yeah.
to Ti. These are in series, right? That
Yes,
is
yes.
clear.
Yes, yes, yes.
Okay, so this is like convection uh, of the rod. Here it's like convection of the ceramic cylinder. Okay, so this is happening between TR and TI. Now similarly, radiation, which doesn't require any air, so it doesn't matter whether convection is happening or not, radiation is going to happen. It will travel from here and it will reach this place. Whether the convection happens or not, it doesn't matter. So what you have to do, the radiation resistance, which is also between TR and TI. Okay, which is what we did here.
Mm-hmm.
So there are two parallel pathways for the heat transfer from the rod, from the electrical rod to the enclosure. Okay,
Right, right.
right,
So now these two circuits are combined into a single one.
right. So how will you combine? You just need to put it in parallel. So you can just take this. You can just draw it as a R radiation. Okay, so you can move this to TR TI. Okay, is that clear now, or is it confusing?
It is a bit confusing.
Okay, so so you one thing you need to notice. So from here the heat has started traveling. Heat is started traveling from the surface. Okay,
Mm.
there are two pathways a heat can travel. So it is same like composite wall. So in last week, uh, when we did the parallel, hmm, so basically in last week this also we did. Is there any other parallel we did? Okay, only thing is this we did, right? So in last week what we did, we have this wood siding. So this is plain wall. So whatever heat comes through here,
Mm.
actually one goes through the stud and one other goes through
Mhm.
the insulation. So there is two pathways for heat,
Mhm.
which corresponds to two different resistance, which is in parallel, right?
Mhm.
Now the same thing you visualize for this. You have heat coming from here, and it has to go here. And now the two pathways are not conduction. One is convection, another is radiation. Okay, so radiation directly goes from one surface to other surface. It doesn't need any medium. So that is what this does. Radiation, it directly goes.
Okay,
So
okay,
some q has gone through radiation. Okay, the other q is going through the convection to infinity, and from infinity again it going through the convection, goes through the
okay.
convection to the other surface. So
Mhm.
that's why you have two convection resistance here, going from tr to ti. Okay, so there are two pathways. One is q radiation pathway. This is q radiation pathway, and the other is q convection pathway. And the convection is actually divided into two more series resistance.
Mhm.
Is that clear now, or?
Yeah, yeah,
So you understand,
yeah,
right? There are two
yeah.
Qs going. One is Q radiation going out, one is Q convection going out. So you should always see from the surface. From surface, what are the two pathways the heat can go out? Okay. So in our previous problem, we had only one pathway. From here, what we had only Q conduction going out. So from here, you had only Q conduction going out. There was no convection, there was no radiation, which is crossing this surface. But in this problem, especially in this rod, from this rod, there is one Q radiation going and there is Q convection going. So when you have two Q pathways, you will have parallel resistance. That's what you have. So total Q which comes out goes through Q convection, and the remaining goes as Q radiation. But it all goes to the same surface, to the other surface Ti. Okay, is that clear? Or
Okay.
so now once it crosses Ti, what happens? That should be straightforward. So from Ti to T naught, how it goes? It is only two Q conduction, right? So from
It is the
it
sitting
is
is there, no?
it is just some material is there,
Material is there.
ceramic material is there.
Ceramic, correct, correct.
Within the material, only Q conduction
This
can go through.
conduction.
So this is the only Q pathway you have. There is no other heat transfer
Mhm.
pathways. Okay, so then you will have only one resistance here,
Yeah.
and then it goes to the outer surface T naught. This is R conduction. Okay, so only thing is here you have, since you have radiation and also you have air enclosed, you have two convection and one radiation. But two convection is in series, because whatever the so whatever the heat which goes from the surface to the infinity can only enter from infinity to infinity to this surface. Okay,
Both through convection.
through convection. So whatever the air has taken, so air when it flows through the rod, it takes some heat out, and whatever heat it took out can only go through the heat. That heat can only go through this surface. So that's why these two resistance are in series,
Yes.
and this Q radiation is independent
Is
of
in
this.
parallel. Parallel.
That's why it is parallel. Okay, all right. So this is what they have asked to found. Label all the temperature, heat rates, and thermal resistance we need to find out. So these are the temperatures, and let's say we will. This is the Q, total Q, and this is Q convection, and here it is Q radiation, and then finally it joins and goes out as Q. Okay, and whatever Q is nothing but your Q generation, which is given as 2 megawatt per meter cube. 2 megawatt per meter cube. Okay, I think you have to multiply it with area, then you will have megawatt per meter per unit area will get. So for this the area would be the,
2 pi r.
will it be 2 pi rl?
Area.
Yeah, but this is for Q generation, right? So what is generating the heat? uh,
That
Rod.
the rod,
Rod,
circular rod,
right? For this,
cylindrical.
so if I want to know the Q coming out of that rod, how should I do it? Q times Q generated times volume of the rod,
Ah, yes.
correct? So what would be the volume of the rod?
Pi r square into sorry, pi r square into L.
Into L. Yeah, wonderful. Pi r square into L is the volume of the rod. Now we don't know the length. We are asked to find for per unit length. So we
So
wanted to
height,
find Q by L.
height, so height 2 are multiplied.
Oh, two. Okay, two is actually 2 megawatt. So 2 into 10 power 6.
Ah,
So it is what is given in the question, right? 2 megawatt per meter cube. So 2 into 10 power 6 is the QG, basically. 2 into 10 power 6 is QG. And V is nothing but pi r square by L. We don't know the length. We are asked to find for per unit length. So we take the L on the other side. So then we will have uh, QG is nothing but 2 into 10 power 6. Q is nothing but 2 into 10 power 6 into pi into r square. Okay. The r would be radius of the uh,
right.
rod, which will be r1. Okay. So
Yes.
this will be Q by L. What we need to find is we want to find surface temperature. So if we want to find surface temperature, what we have to do, we already know the T naught here. We need to find TR here. We know the Q. Okay. Then you know the resistance, total resistance we can find, because parallel and series you can find the total resistance, and then you can find the uh, so once you find the total resistance you can find the surface temperature. Is that clear?
Yeah, yeah, yeah.
Okay, so let's find the total resistance. What would be R total? It will be R conduction plus 1 divided by 1 by R radiation plus 1 divided by R convection rod plus R convection crystal. Is that clear? I directly wrote the total resistance formula. Please let me know if this is not clear. So basically I'm telling these two are in series.
Hmm.
This and this are in series. So this
Hmm.
plus this. So whatever this is nothing but these two are in parallel. So this
Hmm.
plus this into this plus this and this are in parallel. So 1 by R radiation plus 1 by R convection total in the inverse. That will give you the total resistance of this plus this. Okay.
Right.
All right. So let's quickly find out the resistance. What is R conduction? R conduction, since this is the cylindrical ceramic enclosure, we already know it is going to be logarithmic of R3 by R2 divided by 2 pi into KL, but per unit area we are trying to find out. So We already know R3. R3 is 60
60,
by R2 is
20.
20. So let's substitute this 2 pi into K
Okay,
ceramic. K ceramic
1.75.
1.75.
Quarter meter.
1.75 into L, which is 60 by 20 2 divided by 5 divided by 5. So I think it is something around 0.0999 and all. So we can write this as zero point 0.1 Kelvin per watt. We can take per unit length. So L can be 1. So no, don't worry about it. And then R radiation also you can take for per unit length. So it becomes zero point 0.3 Kelvin per watt. Zero point 0.3 is already given. It was just multiplied with length. So we can divide it by length. And R convection rod. Okay. That is, which place is this? R convection rod is this place. This convection. So how will we write that? It will be 1 divided by H convection times area of the surface area, but it will be the rod's surface area. Okay, that is the difference. What would be the rod's surface area? H into 2
2 pi
pi
r.
r.
R,
Which r will be?
N.
The
Up,
rod's r,
up.
r1.
There is 10.
Right. So r1, 10, correct. So you can substitute them here. What is the h is given? To be 20. 20 times 2 pi
2 pi
into 10 mm,
N
which is 10
L.
power minus 3 into L. Similarly, you can find R convection for uh, enclosure, ceramic enclosure, which is 1 divided by area of S of enclosure's inner surface area. So if it is an inner surface area, uh, then what you have to do, the R would be this surface area's R,
20. 20.
20. Yes. So which will be R2 times L is equal to 1 divided by 20 into 2 pi into R2 is 20 into 10 power minus 3 into L. So how much is this coming out to be? These two. So once you find this one is going to be, once you find this one is going to be just the same thing divided by 2. That's it. So is this something like 0.79, 0.796? So I'm getting something like 0.796. Please let me know if this is wrong. And if that is the case, this is going to be 0.398 Kelvin per watt. So once you find all the resistance, you can just find the total resistance, which is going to be zero point 0.1 plus 1 divided by 1 by zero point 0.3 plus 1 divided by 0.796 plus 0.398. How much is this coming out to be? So is this something like 0.339 I'm getting? So I'm just going to write 34 Kelvin per watt. Please let me know if I made any mistakes. Huh? So, and finally you can write Q is nothing but T uh, TR minus T naught, TR minus T naught divided by R total. So we just need to find TR. TR is Q times R total plus T naught. So Q we already know, which is 2 into 10 power 6 into pi into R1 square. 2 into 10 power 6 into pi into R1 is 10 mm, which is 10 into 10 power minus 3 square times R total is 0.34 plus T naught. How much was T naught? 25 degrees Celsius. So let's see what is happening here. 2 into 10 power 6 times pi 10 into 10 power minus 3 into 0.34 plus 3. Were you able to find out the temperature? So I'm getting something like 239 if you round off. Yeah. So basically the rod is at 239 degrees Celsius, but outside the temperature is 25 degrees
25.
Celsius. So which means actually air is a very good insulator. So that is something you can understand. So this air is actually a very good insulator. Even though this, when you have a ceramic enclosure which is 1.75, usually insulating materials will have like 10 power minus 5 watt per meter Kelvin. But here the ceramic enclosure has a very high thermal conductivity. So even though when you have very high thermal conductivity of ceramic material, when you have a air in between this rod and this enclosure, then actually you can have very good insulation. So uh, the temperature is very high here. However, we are not able to feel it, at a distance of 50 mm, which is like 5 centimeter. In a distance of 5 centimeter, we were not able to feel that to 240 degrees Celsius. So that is something you can understand from this. Okay, is that
Okay.
clear?
Yeah, yeah.
Okay. All right. Finally, we have arrived at an spherical tank problem, and this is actually interesting because it is used in the space shuttle. Okay, so a spherical tank is used for storing a liquid oxygen. Is to be made from stainless steel of 0.795 meter of outer diameter and 6 wall thickness. So they are making a spherical tank which is going to hold liquid oxygen, and the spherical tank's diameter and thickness are given. The boiling point and latent heat of vaporization of liquid oxygen is given. The tank is to be installed in a large compartment whose temperature is to be maintained at 240 Kelvin. Okay. Now, what they are doing is you have a spherical tank, and that spherical tank is going to hold liquid oxygen. And we all know the liquid oxygen is actually one of the uh, oxidizer. It's one of the propellant by one of the component of bipropellant used in the liquid rocket engines. So these liquid rocket engines requires both fuel and oxidizer. The fuel will be hydrogen or sometimes methane, and the oxidizer will be liquid oxygen. And the liquid oxygen will be at 90 Kelvin. So after 90 Kelvin, it evaporates. So below 90 Kelvin, it will be in liquid state. So what we are trying to do is we are trying to design a spherical tank which is going to store this liquid oxygen, which can be installed in the space shuttle. Okay, and what they are trying to say is this tank inside it will be 90 Kelvin, and I want to put some insulation on top of this tank such that uh, we will not have any heat coming from outside. So outside temperature is 240 Kelvin, and if the heat enters the tank, what happens? All the liquid oxygen which is present will evaporate, start evaporate, because it is already at 90 Kelvin. 90 Kelvin is the evaporation point. So if the heat enters, 90 Kelvin becomes 91. If it becomes 91, then the liquid oxygen starts evaporating. So we are asked to design a thermal insulation system that will maintain liquid oxygen losses due to boiling below 1 kg per day. So let's say every day, because of some heat, losses, we will have some liquid oxygen to be evaporated. And if some of the liquid oxygen is getting evaporated, let's say I am okay if I have only 1 kg lost in a day. If I'm okay with that, then what would be the insulation uh, thickness that you
Design.
will provide
It is
for the spherical tank, is what they are asking. Okay, so maybe I will draw a diagram so that it will be easy for you to understand. So this is the spherical tank, and our okay, this is the spherical tank. Okay, and then what you have is you have liquid oxygen inside. Now this has some thickness. This is steel tank, right? This has some thickness. Now what we are supposed to do is we have to add this insulation thickness such that my loss is less than 1 kg
per
per
day.
day. So which means what is the amount of heat transfer from, so from outside to inside? Let's say outside temperature is T naught. T naught outside is 240 Kelvin, and T oxygen which is inside Ti, let's say it is 90 Kelvin. Okay, so what happens? The heat flows from outside to inside. Okay, when the heat flows from outside to inside, whatever heat gets in will evaporate the oxygen here.
Yes, sir.
I do not want oxygen more than 1 kg to evaporate in a day. So how
Mhm.
will you calculate the heat?
So that means heat transfer is 213 kilojoule per kg. If it
Right.
is since
It
it
is
is all
one.
up,
Hmm.
latent heat is 213 kilojoule per kg.
Right. So
Maximum that much of heat could be allowed.
okay, wonderful. So that is what it means. So HFG we can write it as latent heat. HFG is 2.13 kilojoules per kg, and I can have only 1 kg per day. So which means uh, m dot, which is 1 kg per day, and the heat can be written as m dot into HFG, which is 1 times 213 into 10 power 3 joules per day. This is the amount of heat I can allow, basically. Okay. So, but we always write heat in watts. So, if I want to convert it into watts, what will happen? This is heat transfer rate. We always write heat transfer rate in watts. How do I convert this into watts? Watts
So
is joules per
for that, so
second.
it should a day. It should be converted into second. That is 3600.
Right. A day contains 24 times 3600.
24 times correct.
Right. So 1 divided by 24 times 60, which is
Yeah.
3600, as you said. And then you can write this as in watts. So this is the maximum amount of heat you can allow. And if this is the heat you can allow, then what you have to do is you just have to find the radius. Then it becomes a simple heat transfer problem. Understood?
Yeah.
So this is given. This is, let's say, R1. Steel thickness we have R2. and then you have R3. So R2 is given, right? R2 is 0.75 by 2, which is point 3, um,
5.
right?
Sorry, 3,
75,
375.
right? 0.375 meters. And R1 is nothing but 6 wall thickness you have to reduce. So it will be R2 minus thickness,
Uh,
which will be 0.369 meters,
yeah,
correct?
yeah, yeah, yeah.
So now we need to just find what is R3. Okay. Um, we can also draw a thermal circuit for this. If I want to draw a thermal circuit, what will happen? Here you can assume that there is no convection between oxygen and internal surface of the steel. Okay. So you can just start from the surface of the internal surface of the steel enclosure or the steel tank. So let's
So,
say,
that means only conduction,
correct, only conduction through the steel
steel
tank
wall.
thickness. Yeah, exactly. So this is one simplification that we are doing actually. But there
Sir,
could be
why we are not considering the air which is just trapped?
uh, so air is not trapped, oxygen we have. So basically what we can have is this oxygen can, this is a liquid, right? So oxygen can move around, and because of that you can have convection here, right? The same thing we saw, air in the, so in the
Yes,
previous
yes,
we
yes.
saw that air is moving, so you can have convection here, right? Similarly, oxygen here can move and we can have convection. There is no problem. But in the question, it was not given. So convection is not given.
Okay,
So I'm just
okay,
assuming convection is not there. But
okay,
you, in default, as you said, you can have. Okay.
okay.
So then you have, there is this conduction, and then you have another conduction through the insulated surface, which we wanted to find out. This is our conduction steel. This is our conduction insulation. So, and then you have outer temperature to be T naught. Okay. Also, what they also said is, you can note here, the tank is to be installed in a large compartment. So the tank is installed in a large compartment in a space shuttle, whose temperature is to be maintained at 240 Kelvin, which means that compartment is maintained at 240 Kelvin, which means the air inside it can be at 240 Kelvin, and also it can flow around these surfaces. Okay, it can flow around these surfaces, and it can also generate some convective heat transfer. It can also have some radiative heat transfer, and all these things are not given in this problem, so I'm just refraining myself from not using it. But if you have a convection from here, then you also will have additionally, uh,
Circuit.
yes, what is it?
Additional thermal resistance circuit.
Right, additional thermal resistance you can have. Okay. So for now, I'm, for simplicity, I'm just assuming that there is no convection around it. Okay, and also in space shuttle you do not have gravity, so unless you blow the air through the fan, you will not have convection, right? The free convection will not happen in space
Mhm.
because we do not have gravity, so we will not have the circulation of air because of free
Yes.
convection. So
Mhm.
gravity and buoyancy is what makes the air to, hot air to rise up and cold air to come down, right?
Right.
uh, but in this case, the hot air, if it gets heated up, it just stays here. In space shuttle, it will not move out because there is no gravity to pull that out, right? So basically you may not have convection, or in some places what they use, they have fans, so fans can be there in, you know, spaces. So in space you can have fan, and it can blow air, and it can, we can have a heat transfer, a convective heat transfer because of that. Or we can also have radiative heat transfer, which is present everywhere. Radiative heat transfer also we can have from the surface. Here I'm just going to take this T naught is nothing but same as the surface temperature. Okay, is that clear?
Mm.
All right, how much is this Q coming out to be? So is it something like 2.465 watts? So I'm getting something like 2.465 watts. Let me know if that is right.
2.4652.
Okay, 4652. All right. So which means that is the heat entering from outside,
Yeah.
correct? Okay, 4652 watts. Now, what I want to find is I wanted to find uh, R3. Okay, so the R conduction due to steel that we know. Now it's a conductive resistance, but in a spherical coordinate. If it is in spherical coordinate, how will the formula change? Resistance we already saw during the lectures. It is 1 by 4 pi k 1 divided by R1 minus 1 divided by R2. So like we had natural log of R2 by R1, here we have a different formula for spherical because it's a spherical tank in three
Mm.
dimension. We have a different formula. Okay, is it clear how we got this formula?
Yeah.
Okay, we have already solved. I mean, we have already derived this formula in the class, so that's why I just took the formula from there. So now the K of steel, okay, K of steel and insulations are not given. So I will write it here. So K of steel is 9.2 watt per meter Kelvin, and K of insulation, usually they will have this foil or some glass material which can provide you insulation. That's what they use it. So that will be in the range of 10 power minus 5 watt per meter Kelvin insulation. Okay. So here if I'm substituting them here, so 1 divided by R1, R1 is 0.369 meters and R2 is 0.375 meters. Okay, this is coming out to be, how much is this coming out to be? It will be very less only. Is it something like 3.75 into 10 power minus 4 watt per meter Kelvin? Sorry.
Yes, I am doing so.
Okay, okay. Something like very small number I got. So this total Q, we can write this as uh, T naught minus Ti divided by uh, addition of these two resistance, right?
So what is the value you got?
3.75 into 10 power minus 4.
I think I have made a mistake. I think
I could also make a mistake. What is the number you have? You have?
I am getting 4.2 into 10 to the minus 5.
Okay.
I think I have made a mistake.
0.375 should, okay. But doesn't matter.
Okay.
We will see. So we have so heat flux we can write it as T naught minus Ti. So which I can write T naught minus Ti divided by R of conduction plus R of conduction due to insulation, right?
Mhm.
This is also we can write it as T naught minus Ti divided by R total. Okay.
Yeah.
Now, so T naught minus Ti we already know, right? This is 240
Two.
Kelvin and this is at 90 Kelvin. Since oxygen is only evaporating, it will maintain the same temperature for 90 Kelvin. Okay.
Mhm.
So if that is the case, what will happen? This will be 240 minus 90
90.
divided by R total, which is equal to Q. We already found out to be 2.4652. 2.4652. So let's find out R total. What is R total? R total is 150 divided by 2.4652. How much is this coming out to be?
This is
60 point
this is
60.85 sometime something around that. Okay. So you see you need a total resistance of 60.85 Kelvin per watt. But this is in the range of like 10 power minus 4 and 10 power minus 5, which is very less, which means everything you have to get it from insulation only, right? So
Mhm.
this is nothing but R conduction due to steel plus R conduction due to insulation, but this is nearly equal to 0, so you can just remove it. You can either keep it or you can remove it, doesn't matter, your equation is not going to change. So you can write this as R conduction due to insulation is nothing but 60.85, which is equal to 1 divided by 4 pi 1 divided by 4 pi K insulation into 1 divided by R2 minus 1 divided by R3. We need to find only R3. We know R2, we know K insulation and everything. So if I reorder it, what will happen? 1 divided by R3 is nothing but 1 by
Six-
R2 minus
16 to
half 60 into 4 pi K insulation,
K
60.8.
insulation.
So K insulation is 1.7 into 10 power minus 5. Substitute that. This is 1 divided by R2 is 0.375 minus 4 pi into 1.7 into 10 power minus 5 into 60.85. So you can find 1 by R3 and then you can invert it. I can take 1 by this. What will happen? So I am getting something like 0.377 meters. So once you solve this, you need to also take reciprocal of this.
Mhm.
So which means the thickness of insulation. How much would be the thickness of insulation?
That is R3 minus R2.
Yeah. Uh, how much would be that?
R2 comes around, R2 is
0.375. So which is around 2 mm.
hmm,
So you need to put a 2 mm insulation of material which has a thermal conductivity of 1.7 into 10 power minus 5 to this, which will make sure you will have only 1 kg of oxygen
20%.
losing per day.
Hmm.
Okay. So this is how you solve a spherical and cylindrical geometry. Is this clear? This is the third
Yeah,
problem.
yeah, yeah.
Okay.
Yes, yes, yes.
So it's just what you need to do is you have to make sure what is the heat transfer happening, whether it's a conduction or convection, and make sure from where to where it is happening. And
Hmm.
based on that, you can just draw a thermal circuit and you can write Q equal to delta T by R, and then problem would be solved. The same thing we did in this second problem also. Only thing is it become a little more complicated because we had a air inside and it is also doing some convection.
Radiation.
Radiation is there. Radiation and two convections are happening.
Hmm,
So
hmm,
here you have one convection, here you have one convection, and this convection is in series, and radiation which is going some
hmm. Directly.
parallelly, right? So you have two things happening in parallel, so that's why you have a little complicated kind of, you know,
Through convection series, and it is parallel with radiation.
radiation, right? So that is the only little bit thing. First one we know it's a critical radius problem.
Hmm.
So if you, yeah, that is what it is. If you do you have any doubts in any of these problems?
No, sir, no, sir.
Okay. And any doubts you have in till now? I think week one and two assignments have been solved, so you can take a look at the solutions also. So if you have any doubts regarding that, also you
So,
can let me
so
know.
the solution is saved.
I think so. Solution is posted, no? No?
In-
I thought solution is posted. Only the answer key came. For some reason, I couldn't log in from here. I will try from my computer. Why am I? But anyway, whether the solution is there or
Okay,
not,
I'll
it's
check it.
fine.
I'll check it.
What you can do is you can let me know if you have any doubts. I will be
Okay, sir. So, what is
available.
your mail, please, sir?
Uh, could you repeat? What is it?
What is your mail, please?
Mail ID? Okay, I will put it in my uh, in the chat. Yeah, I hope you received it.
So,
So it's Ganesh KV at iitgn.ac.in. Okay, so
just a second,
you
sir.
can mail also. Uh, the
Just
easier
a,
way is you can just come and ask questions in this class
uh,
itself. So
so could you please show it to one second, Ganesh?
so I just posted in the messages. Can you check the
Okay,
message?
okay.
Is it? Did you receive it in the message? Check the messages of this Google Meet. You will get,
Okay, I'll check it.
or I will just write it here. Ganesh KV at the rate iitgn dot ac dot in. Okay,
IIT Gandhinagar.
Gandhinagar. Yeah, IITGN.
SC.in.
Okay,
Right,
so
right.
you can email, or you can just come next week if you have doubts, and I will be able to solve it for you.
Okay,
Okay.
right, right.
All right.
Okay, thank
If
you,
there
sir.
are no doubts, then I will see you in next week. So probably I will stay here for another 10-15 minutes. If someone wants to join and ask, I will be available for them. Um, but I'm not going to teach anything new. So if you have any doubts, feel free to stay back and ask. If not, I will see you in next week. Okay?
Thank you, sir. I think nobody is here with us.
Yeah, 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 yeah. I think everyone joined and then it's done and then they left. All right.
Thank
All
you,
right.
sir.
Thank
Bye.
you. Thanks for joining, Basan channel.
Thank you, sir. Bye.
Bye bye.